Wow. Put the phone carefully, not push me. Don't move it. Push it. Okay. Good morning, my dear students. I'm Archie Francis Devan. Welcome to AFD'S Academy. So today we are going to carry out revision on volumetric analysis calculations generally, and everything that has to do with volumetric analysis. It is very important that if we get ourselves acquainted with these realities, we'll be able to sustain and survive in the world of chemistry. So today, like I said, I'm going to carry out revision generally. So in volumetric analysis generally, which has to do with the titration, which has to do with acid-base, and that reaction is known as neutralization reaction, the reaction between acid and bases, which gives us salt and water. But along the line, for us to be able to achieve this, there are certain procedures which we must take note, and it is very important. For example, we need a particular acid, we need a particular base. Before we engage in a titration, the color will change to give us our endpoint, which is what? That depends on the indicator used. So take note of the very important. When we are using these indicators, for example, methyl orange, first of all, you are going to pipette out your base into your conical flask, 25 or 20 ml, drop your indicator. Since it is a base therein, the color of the indicator have to reflect. If it is methyl orange, it's going to be orange in color, all right? Orange or yellow in color. Then when titration commences, at the end point, the color changes to pink. If you are using what? Methyl orange. The color changes from what? The orange to pink. But if you are using phenolphthalein, it changes from pink to colorless. Don't forget that. But before we proceed in the process of carrying out the titrational analysis, you must have to prepare your acid. It is toxic. So it definitely means that it has a specific place where it has to be prepared, where we prepare it in the fume cupboard. Do not forget, where we prepare toxic substances in the what? Fume cupboard. Then at the same time, the precautionary measures that must be taken when you're carrying out what volumetric analysis. First of all, ensure your burette is wrecked, rinse your conical flask, your burette, ensure all the apparatus with distilled water before you commence it. Make sure you remove all air bubbles in the pipette and the burette. Make sure you use 2 or 3 drops of what? Indicator, and so on and so forth, a whole lot of that. So I've given us the basics of what we need, but for today, we are going to engage on the various calculations that will guide us to achieve what we want. So if you get the adequate calculations perfectly and the formulas required, you wouldn't have much challenges. I've given us a variety of formulas. For example, concentration, I say it could be mass concentration over relative molecular mass. And the same concentration can be also gotten by using our CAVA, CBVB. In this principle, that can also be achieved. Remember, we say amount is molar count times volume, which means concentration can be what? Amount over volume. And that same amount is mass over relative molecular mass. Percentage purity is the mass count of pure over that of impure times 100. Percentage impurity is the mass count of impure minus pure over impure times 100. And also, very important, mass count of pure plus mass count, percentage purity plus percentage impurity equals to 100. and relative molecular mass can be mass count over molar concentration, and a whole lot of them. All of these things, if we remember our formulas, we can put them into good use. Mass concentration can be molar constant relative molecular mass. It can also be mass in gram over volume in DNQ, which means that if the volume is in CNQ, you convert it to DNQ by dividing it by what? 1000. That is how important that is. So, having given you a collection of all the formulas, we're just going to engage in what? The calculations directly. Let's see what we can achieve. It is important you pay attention to the calculations in case any day, anytime you come across them, we don't have any challenge. For those of you who haven't subscribed, please do subscribe. It is important so that you'll be able to get all my videos whenever I have them uploaded at ease, at the convenience of your home. So let's take our first question. We say, I'll read it out, then solve it, all right? We say A is a solution containing 14.0 GDMQ of potassium hydrogen tetrazosulfate 6. Know that GDMQ, wherever you come across that, it is the mass concentration we're referring to. And in that solution, we have the volume of the base is being 25, and that of the acid is 24. And the reaction is between potassium hydrogen tetrazosulfate 6, which is an acidic salt, with the base, which is sodium hydroxide. So I'm going to list the given out. That is what I will do. Then we solve it together, all right? So let's see the given. Okay, so I'll call them the given. A for the acid, potassium hydrogen tetrazosulfate 6. And B for the base, which is sodium hydroxide. We say the volume of the base is 25 cm3, and the volume of the acid is 24 cm3. And the mass concentration of the acid, so in terms of mass concentration, I wouldn't be writing mass concentration, it's going to be too lengthy, so I'll just write the unit for it, so I will be able to remember. So call it GDMQ is the mass concentration, and that is 14.0 GDMQ. So having carried out the titration analysis, the variables are given. We are meant to calculate certain things. The concentration of acid in mole per DNQ. Concentration of acid in mole per DNQ. But before we proceed in calculating the concentration of the acid, we must have to get our equation of reaction, then we proceed. So I have my potassium hydrogen SO4 reacting with sodium hydroxide. All of them in aqueous, allow me to put that. We have our sodium sulfate, sodium sulfate plus potassium sulfate plus water. So for this to happen means we're having 2 moles here of potassium, then we have our 2 here. And sodium here is obviously going to be 2, and here we're still also going to have 2. But let's check if what we need is balanced. 2 sulfate, 2 sulfate, 2 sodium, 2 sodium, 2 potassium, 2 potassium. Water, we have 2 here plus 2, 4. So I have my 2 here. So my equation is balanced. So by virtue of that, I will have number of moles of acid to be 2 and number of moles of base to be 2. I can take out the formula, the equation of reaction, so that I can proceed with the other stuff. All right, remember we're looking for the concentration of the acidic salt in mole per DNQ. What is the formula for concentration? We say concentration is what? Amount over volume. So if you look here, you realize that we do not have anything amount given, so that formula cannot be used. And we also have the concentration to be the CAVA formula. If you look here, the concentration of the base is not given, so that formula also cannot be used. We also have molar count to be what? Mass concentration of our relative molecular mass. Now, the mass concentration of the acid or acidic salt is given. the relative molecular mass can be gotten from here. So that is the only formula we can use in this category or in this sense to get the molar concentration of what they require. So I'm going to take this out. I can leave it, no problem. So here, molar count of A becomes mass count of A over relative molecular mass of A. Now, the mass count of A is given here to be 14, so I will have 14.0 GDMQ. But what about the relative molecular mass? So we are going to calculate it. Permit me if I have to use this page. I have KHSO4, potassium is 39, hydrogen is 1, sulfur is 32, oxygen is 16 times 4. So 16 times 4 is 64 plus 33, 33 plus 39. So I have 136 G mole. The unit is very important. So my relative molecular mass of potassium hydrogen tetraoxide 6 is what? 136. So this will be over 136 G mole. And when I finalize this, what am I going to get? 14 divided by 136 will give me 0.1029. Approximately to 3 significant figure, I have 0.103. 0.103 mole per dNq. So we've answered our first question, which is what? The molar concentration of the A acid. So this is it. So I'm going to put it here so that when it is required further, I'm still going to use it. So this I can take out and take the equation of reaction out. And now I have my concentration of the acid to be 0.103 mole per dNq. Now, what's the next question? It says that we should calculate the concentration of B in GDMQ. So the concentration of the base in GDMQ. Now, let's go through the formulas, all right? Again, which is the mass concentration. The mass count, formula for mass count, is molar count times relative molecular mass. Now, we can get the relative molecular mass here, but the molar count is not gotten, it's not here. But then there is something we can do. We have the concentration of the acid, which is this, 0.103. If we look for the concentration of the base, then we can use that formula, which is molar count times relative molecular mass. So definitely, we have this for the acid. We can use our CAVE to get out of what? The base. And once we've gotten out of the base, we can proceed further to get what? The mass concentration. Other formulas are not viable in this sense because mass concentration can also be mass over volume, and there is no mass for the base, although the volume is there, so that cannot be used, and so on and so forth. So let's proceed. I'm going to take this out by now. I believe it must have been done right now. So I'm going to take this out so that we can proceed to get the molar count of the base. Then we now go straight to what? The required question. So the questions sometimes are not direct. You should always understand that. All right, now let me call this 2, although they didn't ask us of this, but it is a basic requirement which can only aid us to get what we need. So concentration of the, let me call it molar count of B. This can be gotten by using the formula CAVA over CBVB is equals to NA over NB. Now, what am I looking for? I'm looking for the concentration of the base. So if I make that the subject of formula, I have my CB is equals to CAVANB over VBNB. And this is equal to the concentration of the acid just gotten is 0.103 mole per dm³ times volume of the acid is given to be 24. So I have 24 cm³ times number of moles of the base, Nb, is 2. And this is all over. I have volume of the base. Volume of the base is 25 cm³ times number of moles of the acid, Na, is 2. So if I evaluate this, what am I going to get? Let's see. 0.103 times 24 times 2, which is that. Divide by, this is 50. 50, I will have 0.0999. Okay, that is it. Oh, come on, I have 0.0989. This is it. Now the unit is mole per dm³. Now, in this sense, I have gotten my concentration of the base. So I'm going to write it as Cb, which is 0.0989 mole per dm³. So having gotten this, now we go back to the main question. We should get the mass concentration of what? The base. The mass concentration, which can now become molar comm times relative molecular mass. So that's how we go about it. So I'm going to take this out to now answer what is required of me. So let me take this and we go about solving the last one. So I have my third question, which is mass comm of B. And mass comm of B is molar comm of B times relative molecular mass of B. So now I will take out this so that I can substitute the variables in it. So let me take this out. Okay, now what is my molar comm? My molar comm of the base is 0.0989 mole per dm³ times relative molecular mass of the base is 40 g mole. And this times 40 is 3.56. Let's call it so. 3.56 relative GDM³, the mass concentration. So this is our answer, what was required. So although we have to move in a roundabout manner to get what is required, sometimes the questions could be that technical. Now, most of us may be asking, how do we get this 40? Is the relative molecular mass of the base, which is this. The relative molecular mass of the base, sodium is 23, plus oxygen is 16, plus hydrogen is 1. If you add all of these, you have 40 g mole. So that's how we got that. So this is it. Now we're going to take another question. We have a couple of questions we're going to solve. A broad spectrum of what calculation of questions, so that when you come across any of them, you'll be able to deal with them without hesitation. So question number 2. Let me take out this so that I can state our given again. So question number 2 says, let me read it, then I'll give us the given. A is 0.125 mole per dm cube of tetrazosulfate 6 acid. B is a solution containing X GDM cube of sodium hydroxide. That 25 cm cube of B gives us 23 cm cube of A. If the equation of reaction is this, which has been given, we should calculate the amount of the base, of the acid, concentration of the base, and the value of X. So let me write out the given. Let's call this A, H2SO4. And my B is the sodium hydroxide. So let's see. A is 0.125 mole per dm cube. Mole per dm cube is the concentration of the acid. That's the unit for molar count. 0.125 mole per dm cube. And VA is given to be 23 at the end of the endpoint. It was 23. While here we have X GDM cube is given, and the volume of the base is 25 cm cube. Okay, we have to balance the equation, then we proceed further. So, if this is what we have, let's see our equation. H2SO4 plus sodium hydroxide. This gives us sodium sulfate plus water. So we're going to check it out. One sodium, water is okay. If I have 4 here, I'm definitely going to have 2 here, and I'll have my 2 here. So the number of moles of acid is 1, and the number of moles of base is 2. So from the equation of reaction, all of them are in their aqueous state. Water is liquid. So I don't want to waste time putting all of that. Now, this is it. What did they say we should do? Let's look at it again. They say we should calculate amount of the acid. Now, this is my stuff. What is amount? Amount, we have the formula known as mass over relative molecular mass. There is no mass given here for acid, so that formula is not applicable. Amount can also become molar count. It's also molar count times relative, times volume. Now, molar count times volume. The molar count is given, and the volume here is also given. So we can use that formula to get what our amount as required. So let's now say A is amount of A, which is molar count of A times volume of A. Remember, the volume is in dm cube, so which means whatever the volume is here in cm cube must be converted to what? Dm cube. Now, the molar count is 0.125 mole per dm cube times the volume is 23 of the base. 23 over 1000. I put my dm cube outside. So this is still 0.125 mole per dm cube times. So we have 23 divided by 1000. Well, let's take 0.023. So we have 0.023 dm cube. Now, when we multiply that with base times 0.125, we are having 0.00288, approximately 288 mole. Now, how is it mole? Because dmq raised to power minus 3 times dmq raised to power 3 is 0. Minus 3 plus 3 is 0. Remember indices. If I take this out, we say when numbers with equal bases are multiplied, their powers are added. So when you add their powers, minus 3 plus 3 is 0. So that is it. In zero law of indices, anything raised to power 0 is 1. 1 times mole is mole. So that's why our unit here is in mole. So here we have gotten what we need. You see, one thing which is very important and significant is your ability to remember the formulas. If you do not remember the formulas, then how are you going to survive? It will become difficult, you understand? So you must memorize all the formulas, then you will be very fine. Let's take the second one, concentration of B in mole per dmq. Yes, concentration of B. Now, we have the concentration of A. For us to get the concentration of V, which is Cb, will be much easier. So we use what? The formula CAVA. That is a direct question. CAVA to get what we want. So I'm going to take this out so that we can now get the concentration of the word B's. All right, number 2, concentration of B in mole per dmq. We are going to use CAVA over CBVE is equals to NA over NB. If that is true, then I'm looking for CB, so my CB is equals to CAVA NB over VB NA. And this is concentration of the acid, which I've gotten already. Okay, it was given is 0.125 mole per dmq times volume of the acid is 23 cm3, 23 cm3 times number of moles of the base is 2 all over volume of the base is 25 times number of moles of acid, Na is 1. So my CD will become 0.125 times 23 times 2 divided by 25, 0.23. So I have 0.23 mole, 23, 3 significant figure, 0 mole per dmq. So I come back here, I have 0.230 mole per dmq. Okay, let's see then what is required again. We've gotten that. Now the last one is the value of x. Remember the x here, xgdmq. So they are asking us of the value of x. Definitely they are asking us of what the mass concentration of the base. All right, so I'm going to take this out so that we're going to get the mass con. What are the formulas again? Remember, we say mass over volume, which is not required in this case, but mass concentration can still be what? Molar con times relative molecular mass. I have my molar con here, and the relative molecular mass can be gotten from here being 40. So by virtue of this second formula, I can achieve that. So let's see how to get the mass concentration of the base. All right, that should be the third question. Mass con of B is equals to the molar con of B times relative molecular mass of B. So the molar count of V is 0.230 mole per dm cube. And the relative molecular mass is 40 G mole. Remember, I told us how to calculate the relative molecular mass. It's important you don't forget that. 0.230 times 40 is equals to 9.2. So I will be having 9.20 GDN cube. So by virtue of base, I've been able to get what? The mass concentration of the base. So these things are very important. I wouldn't just remember how to do that if I don't know the formulas, if I don't have the formulas offhand. So it is important you have the formulas offhand. All right, so we're going to take our third question, but this time around the question is going to be on the relative molecular mass. You're going to give me a minute. I'll be back while you write this. Okay, let's proceed. Now, our third question says, A is a solution containing 3.7 GDM cube of an acid, H2X. So the acid is H2X. We don't know what X is. We're going to find out. B contains 2.15 gram of sodium hydroxide per 250 cm cube of solution. That which, when we carry out our titration, the volume of the base should be 25 cm cube, and that of the acid was gotten to the, which is the endpoint, to be 26.60. Now, from those variables, we should be able to calculate the concentration of solution B, that of A, molar mass of the H2X, and so on. So let's take out the given first. Let me state the given. So I'm going to claim this. Okay, we say A is H2X. H2X. And A contains GDN cube, they give us the mass concentration is 3.7 GDN cube. B contains, this is B, contains 2.15 gram in 250 cm cube of solution. That we should put solution of the base, that is NaOH. And when we do that, we have 25 cm cube for the volume of the base, and we have volume of the acid to be 6.6 cm cube. After all of that, we should calculate the concentration of B in mole per dm cube. So let's go back. Now we have sodium hydroxide plus H2X, which is, we're going to have sodium X plus water. So we're going to balance it. We have 2 hydrogen plus 1, 3. Here is 2. So if I add 2 here, I have 4. And I definitely have to add 2 here, I have 4. Now, sodium is now 2. So sodium is 2. Oxygen is 2 now. Oxygen is 2. I think everything is balanced. So the number of moles of acid is 1. And the number of moles of base is 2. Now, we don't know what this is. We are going to, if it is required, I think we'll find out. So we've gotten this. Now they're asking us to get the molar concentration, let's see what they're asking us to do. Now, from the equation of reaction given, 2 moles of water, okay? From the result and the information provided, calculate the concentration of solution B. All right. Concentration of solution B in mole per dm3. So now we're looking for the molar count of the base. Now, if you check, we don't have Ca, we don't have Cb, and we need to get Cb, and the variables given are just all of that. So we have to review the various formulas to see the most appropriate to be used. Now, the molar count, we can get it through CAVE, but in this case, Ca is not given. Now, the molar count also can be gotten through mass count over relative molecular mass. The mass count is technically given. We have to derive it from whatever we have here, and then the relative molecular mass is there. So how do we do that? The mass concentration, remember I said that the definition for mass concentration is also mass over volume. So which means we are going to use that formula to get the mass over volume, but the volume is in dm3, which means we convert the 250 cm3 to what dm3. So we can get our mass concentration. If we get our mass concentration, then molar count becomes mass count over the relative molecular mass. So let's proceed first of all to get what? The mass concentration of the base. Now I have my one. Mass count of B is mass in gram over volume in dm3. Now the mass in gram is 2.15 gram over the volume is 250 cm3. That's divided by 1000, and put my dm3 here. Okay, and this is equals to 2.15 gram over 250 divided by 1000, 0.25 dm3, which is equals to, now 2.15 divided by 0.25 is 8.6. So this is 8.60 GDMQ. So now I have my mass concentration, so I'm going to call it GDMQ. Now is 8.60 GDMQ. So now this is what I have. So let's proceed further. Now we want to go into the question. The question says the molar concentration of the base. I want to now get that. So this was a distraction. If we do not know that formula, we can't get there. So it is important we have them all. So let me take that now. The main question now comes. Molar count of B, which can be gotten by saying mass concentration, mass count of B over relative molecular mass of B. And mass count of B is 8.60 GDMQ over the relative molecular mass is 40. I've calculated that before, G mole. And this is equals to my 8.6 divided by 40 is equal to 0.215. So I have 0.215 mole per dmq. So I'm going to write it down. My CB now, sorry, is 0.215 mole per dmq. Let's see the next question. Okay, that's question number 3. Okay, from the result, concentration of B mole per concentration of A in mole per dmq. That's what we need now. Now we've gotten our CB. For us to get our CA will be easier. We apply what is CAVA formula and we move. So let's see how that works. Okay, let me take that up. Now I want to get my CA. So for CA, that's 2 now. For me to get the comp of A in mole per dm3, I'll definitely use the formula CAPA over CBVB is equal to NA over NB. Why? Because the concentration of the base is already gotten. So if I do this, let's see what we get. So I want to make Ca the subject. So my Ca is equals to CBVBNA over VANB. And this is equals to, the CB is 0.215 mole per dm cube times VB, volume of the base, is 25 times number of moles of acid from the equation of reaction is 1 times all over volume of the acid is 26.6 cm3 times number of moles of the base NB. Where are you? NB is 2. So and this is equals to, let's see, 0.215 times 25 divided by 26.6, and so there we have 0.101. This is 0.101 mole per dm. So this is the concentration of the acids. Ca is 0.101 mole per dm. Now, what is the last question? B. Now, 2, concentration of solution A, then the molar mass of the acid. Now, for us to get the molar mass, remember molar mass is mass concentration over relative molecular mass over molar concentration. Mass concentration over molar concentration, that is the formula for relative molecular mass. So the mass concentration is given, the molar concentration is gotten, so we can now use that formula to get what the relative molecular mass of the acid. So let's see, we want to know the relative molecular mass of that. I can take this out now. Now, the third question says the relative molecular mass of A is mass com of A over molar com of A. And the mass count of A is given to be 3.70 GDN2 over the molar count of the acid is 0.101, okay, mole per dm. And this is equals to 3.7 divided by 0.101 is equals to 36.6. 36.6. The relative molecular mass is G mole. All right. The dm cube will cancel itself. Is gram per mole left. So 36.6 is the relative molecular mass of the acid. So if that is true, what is X? You may be required to do that. Although it's not given here, but in case of necessity, I think we'll come across questions that may require that. Now, what is X? It's simple. We say that the relative molecular mass, the acid is this. If A is H2X equals to 36.6, and this is 2 plus X equals to 36.6. X is equal to 6.6 minus 2, S is 34.6. So that is our value of X. Now, if you put that, I don't know which compound have that, put it down, that is what is expected. So we are going to take another question. Like I said, we're going to solve important questions so that you should not forget how to deal with them when you come across them. So let's take another question. We say A is a solution of hydrochloric acid containing 7.30 GDMQ. B is a solution of X2CO3 containing 10.6 GDMQ. So the mass concentration of the acid and that of the base have been given. Now when we put A into the burette and titrate it against B, the end point of the reaction is gotten to be 25. Oh, that's interesting. Why the volume of the acid is also 25. From that information, we should calculate the concentration of A in mole per GNQ, count of B in mole per GNQ, molar mass of X2CO3. So let me write them out. All right, let's take this out. Okay, we say A is HCl and B is X2CO3. A is a solution of HCl containing 7.30, so the GDMQ of A is 7.30. B is a solution of X2CO3 containing 10.60. So the GDMQ of B is 10.60 GDMQ. Now when we put that and titrate, the volume of the base is 25 CIQ and that of the acids is also 25 CIQ. Now, okay, at the end of the day, we are bound to calculate. Let's balance the equation first. We have HCl plus X2CO3. We are getting X chloride plus water plus CO2. Now we balance. We have 2 hydrogen, we have 1 hydrogen. So if I have 2 here, my hydrogen is balanced. I have 2 and I have 2. I have 2 chlorine, I have 1 chlorine. And I have 1 X, I have 2 X. So if I put 2 here, I have 2 X and 2 chlorine. That is also balanced. I have water is 2, hydrogen 2, oxygen now is 3, 1 plus 2, 3. So my equation is balanced. So my number of moles of acid here is 2, and my number of moles of base NB is 1. Now from here, the question comes. Let's see. Calculate the concentration of A in mole per GNQ. 1. Count of A in mole per GNQ. Now, concentration, mole per GNQ. How do we go about that? Remember, we say we can use CAVA to get that, but the concentration of the acid is not given, that of the base is not given, so that formula cannot be used. Now, molar count, which is also amount over volume, there is no amount given. And the same molar count is mass count over relative molecular mass. So the mass count of the acid is here, which is this. The relative molecular mass can be gotten from it. So that is the formula we can use. So I would say count of A mole per GNQ is equals to mass count of A over relative molecular mass of A. And we move on to say the mass count of A is 7.30 GDMQ over the relative molecular mass of this is 36.5 g mole. How do we get that? HCl, hydrogen is 1, plus chlorine is 35.5. That's the mass number. That gives us 36.5. So, if that is true, let us see what we have. We have 7.30 divided by 36.5. That is 0.2. Again, let me check it again. 7.3, where is it? 7.3 divided by 36.5, that is 0.2. So the molar count of the acid is 2, we add 0.0 mole per dm. Now the question is why 0.0? Like I told us a couple of times that the molar concentration, in chemistry, the value must be in 3 significant figures. So this is 200. So I can come over here now and take this equation of reaction out. You've got what we want there. And now I have my Ca is 0.200 mole per dm3. Next question says concentration of B in mole per dm3. Okay. Now, for concentration of B in mole per dm3, we cannot use this same formula for that. Why? Because the relative molecular mass is not complete. This is X. X is unknown. We don't know what X is. So this formula cannot apply to this. So how do we get that? We have to use the CAVA. Since we've gotten our concentration of the acid, which is here, we use our CAVA to get the count of the base. So permit me to take this out so I can apply that to see what we get. Okay, now we go. Number 2, count of B in mole per dm3. We're going to use CAVA over CBVB is equals to NA over NB. So that is it. Now I'm looking for CB. I'm going to make use of, make CB the subject of formula. Remember, this change of subject formula is very important. It's a topic in mathematics. You need to go through it, go study it. It's very important. Otherwise, you're going to find it difficult to move around your chemistry, your physics, and even your mathematics. It's one of the most important topics in mathematics that you cannot take for granted because it is 100% needed in chemistry and physics. So if you do not know how to make your CV the subject, that's a problem of its own, unless maybe someday, sometime, I may likely just take that topic in maths so I'll be able to transfer most of these things. And you owe yourself the duty to go through all of that, to study, to know, because the reason why you're here is to study, isn't it? So now we have our CV as a subject. Now, if my CV is this, so this goes with this, which is CAVANB over VBNA. Most of you will like, how do you get there? My job today is not to teach you how to do change your subject because I believe you're supposed to have known it by now. We do cross multiplication, this time is this, we keep it by the side, this time is this, we keep it by the side, we look for what we are looking for, CV, we divide both sides by what is close to it, and this is what you're going to get. So, great time to do that. So now, concentration of the acid is gotten to be 0.2. So I have 0.2 mole per dm3 times volume of the acid, VA, is 25 cm3, times number of moles of the base, NB, where are you? Is 1. All over, volume of the base is 25, times number of moles of the acid, Na, is 2. So, this is equals to, I know 25 can cancel out, so 0.2 divided by 2. So I have 0.2 divided by 2, and that gives us 0.1. So 0.100 mole per dm3. Okay. Okay. There we are. We have the last one is the molar mass of the base. That. Now, how do we get the molar mass? Remember, I told us that molar mass can also be given as the mass concentration over the molar concentration. All right, the mass concentration over the molar concentration. That is it. So let's see how we can do that. I guess I can take this out. So we'll take the third question. So the third question here says molar mass of B. Molar mass is equals to mass com of B over molar com of B. So let's do. Now, what is the mass com of B? The mass com of B is given to be 10.6. So 10.6 GDNQ. The molar com of B. Whoa. Okay, I don't know. CB. Okay, it was 0.1. 0.100 mole per day. Is 0.100 mole per day. And this is equals to 10.6. 6 divided by 0.1 is 106. 106 G mole. So here I have 106, the G mole, which is the related molecular mass is 106 G mole. So that's all about what is required of us. But I always add a bonus. Now we've gotten the molar com, the related molecular mass of B. What if you are being asked again to find the value of X? It is not included here in the question, but let's take it as a bonus in case of necessity. I always take note of the necessities. All right, let's go down to see what we can do. Taking this out. Okay, we say that X2CO3 is equals to 106. This is X times 2 plus carbon is 12 plus oxygen is 16 times 3 is equals to 106. 2X plus 12 plus 48 is equals to 106. All right, let's see. 48 plus 12 is equals to 60. So I have 2x plus 60 is equals to 106. So 2x is equals to 106 minus 60. Okay. Now, 106 minus 60 is 46. So 2x is equals to 46. Divide both sides by 2. X is equals to 23. It therefore means that this compound is Na2CO3. 23, the mass number of the element that has 23 is sodium. So it is very important we take note. Okay, those are bonuses, and like I said, I must always add bonuses so that in case you come across something like that, you should not be too shocked or surprised. So you should also know the relative molecular masses of at least your first 20 elements. So by virtue of that, if you have 23 as X, you ask yourself which element have that what mass number. That is sodium. And if it is sodium, you put it into the formula. So the question may be, find the value of X. Okay, the value of X is 23. State the element, the ring. The element is sodium, and so on and so forth. We are going to take maybe 1 or 2 questions on percentage purity, then we'll touch water crystallization, then we can shut down, because by that, I believe you must have touched all the essential areas. Do not forget, from the beginning, I told us, in the course of we preparing our acid and base for us to carry out our volumetric analysis, we carry out the toxic substances that are prepared in the fume cupboard or fume hood, and we use our burette for the acid that are prepared for the base. When we use methyl orange, we have an orange color in the alkaline medium and pink in the acidic medium. It changes to pink. And we have a reddish or pink color when we use phenolphthalein in the alkaline medium, and it changes to colorless in the acidic medium. All those things are very important. And there are, I don't know, but they have to prepare the reagents. It's not important for the time being. I have a topic that treated that, so you can check in my channel, preparation of reagent, the solid and liquid substances. You see those formulas in case anything of sort happen to come your way. You will not be too shocked or surprised. Let's move forward. I'm going to take this out. Our next question. Okay, percentage purity. A is a solution containing, so this is my A. It's a solution containing impure ethane diode acid, H2C2O4. Impure ethane, so we have 6.30 gram of impure H2C2O4. So the mass of, is that GTMP, sorry. So the mass count of the impure ethane diode acid is given to be 6.3. Now, what is the formula for percentage purity? We say the mass concentration of pure over the mass concentration of the impure times 100 is the formula for percentage purity. And you see, they're giving us for impure means we must certainly get the mass concentration of the pure. And if you want to get percentage impurity, the formula could be mass count of impure minus mass count of pure over mass count of impure times 100. You get your percentage impurity. So, and also we say percentage purity plus percentage impurity is equal to 100. So if you have your percentage purity, you can make the impurity the subject to get that of what? Impurity. Don't forget those, they are very important. Now, we say B is CB 0.10 mole per dn cube of sodium hydroxide of NaOH. Okay, we say we should use 25 cm cube of the base. Volume of the base is 25 cm cube. And when we do that, we get the volume of the acid Va to be 20.57 cm cube at the end of the titration. From the equation of reaction given, which is H2C2O4 plus sodium hydroxide, gives us Na2C2O4 plus water. All right, so this is it. They say we should calculate the concentration of solution A in mole per dn cube. concentration of solution A in mole per dm³. So from the equation of reaction, okay, let me be sure what they have here is 2. All right. So the number of moles of acid is 1, and the number of moles of base is 2. So from the equation of reaction, we can now deduce on how to get what is required of us. If we use CABA formula, we are going to get a C. CB is given, then we can get our CA from that formula. So let's start. Molar count of A. We use the formula CAVA over CBVB is equals to NA over NB. And we're looking for CA, so my CA is equals to CBVBNA over VANB. And this is equals to, all right, concentration of the base is given to be 0.100 mole per dm³ times volume of the base is 25 times number of moles of the acid is 1 all over volume of the acid is 20.57 cm³ times number of moles of the base NB is 2, and this is equals to, let's see, 0.1 times 25 divided by 20.57 divided by 2, 0.0608. We have 0.0608 mole per dm. So the concentration of the acid is 0.0608. So let me take this out so that I can put that in. So my CA, 0.0608 mole per dm³. Next question. It says concentration of solution A in GDM³. Remember, like I told us earlier on, we're going to know the mass concentration of the word impure is given. We have to calculate that of pure. It's a good one that I don't tell you, but you just know what to do. The mass concentration of the pure, mass concentration is molar count. Where is it? Molar count times relative molecular mass. So when we use that, we'll get the mass concentration of pure. But remember, the mass concentration of pure must be lower than that of impure. Anytime, any day, your mass concentration of pure is higher than that of impure, then you're wrong, because a substance contains impurity. The mass of those impurities are also included. By virtue of that, it should be higher when it is now pure, because the impurity must have been removed. So let's find out if that is true to get the mass concentration of the pure, so that we can see. Next, we'll see mass count of pure ethane dioxide acid is molar concentration, molar count times relative molecular mass. The molar count is 0.0608. All right, yeah, mole per dm³ times 90 g mole. How do we get 90? The relative molecular mass of the acid. So we come back here, we have H2C2O4. Hydrogen is 1 times 2 is 2, plus carbon is 12 times 2, 24 plus 64. 24 plus 64 plus 2. Okay, 88, 89, 90. So that's how we got 90 g mole for the relative molecular mass of the acids, ethane dioxide acid. So when I multiply that, 0.0608 times 90, 5.47. So 5.47 GDNQ of A. So it is true that the mass count of this is lower than this. So it means we are on the right track. Then we continue, we proceed. Now let's see if this is true. What is the next question? We should be looking for, where is it? And hence percentage purity. Now the next one is to get a percentage purity. So let me call this GDNQ of pure is 5.47. So I'm going to take this out so that we can calculate the percentage purity. Now, the last question. Percentage purity is equals to mass count of pure over mass count of impure acid times 100. And this is pure is 5.47, impure is 6.30 times 100. And our answer is, I want to see how many, what the percentage is. 5.47 divided by 6.3 times 100. It is 6.8% pure. It is 6.8% pure. So it's very, very pure. Now, if you were to be asked, what is the percentage impurity? Remember, I told us that we have a formula which is percentage purity plus percentage impurity is equal to 100. So if the percentage purity is 86.2, what is percentage impurity, which is 100 minus 86.2, 100 minus 86.2, 86.8, sorry, 100 minus 86.8 will give us 13.2. So the percentage impurity is 13.2. So you don't need to be told, but you should just know how that can be gotten. Okay, this same question, you may be asked to calculate the percentage impurity, not that of purity, which means you're going to still run it through this way and you get it, or you say percentage impurity minus purity over percentage impurity times 100. That can also give you that. All right, let's take one more impurity, then we'll go to water of crystallization. And that is where we can shut it down. Okay. A is a solution of HCl containing 5.00 GDNQ. B is a solution of impure potassium hydroxide containing 6.50 GDNQ. Okay, let me take this out first. A is, let's say, HCl. All right, let's take it. A is a solution of HCl containing 5.0 GDNQ. So the GDNQ of the acid, hydrochloric acid, is 5.00 GDNQ. B is a solution of impure potassium hydroxide. B is potassium hydroxide. Say it's impure, containing 6.5 GDNQ of impure is 6.5. 6.50 GDMP. In a titration exercise, 25 of B, so volume of the base is 25 cm3. And the end point, which is the volume of the acid, is 19.10. 19.10, let's call it 1 cm3. Was carried out. We should calculate concentration of A. So before we move on to start doing those calculations, we have to balance our equation so that we can get our NA and our NB. But remember, the percentage, the substance that is impure in this case is the base. In the previous was the ethanediol acid, which is the acid. Now it is the base, which means that any substance can be impure. All right? So you shouldn't just be said it is just the acid. So we are balancing our equation. We have potassium hydroxide plus HCl will give us potassium chloride plus water. 2 hydrogen, 1 oxygen, I think that's it. Na is 1 and my Nb is 1. So if that is true, let's proceed. Let's take first question. We should calculate concentration of A in mole per dm³. Now we want to calculate the concentration of the acid in mole per dm³. All right. Now, how do we do that? The concentration of the base is not given, but we have the mass concentration of the acid is given. So we can use the formula. The CFDA cannot be used, but we can use molar count, which is equal to mass count over relative molecular mass, and we'll get that. So let's come down. We see molar count of A can be gotten by saying we use mass count of A over relative molecular mass of A. The mass count is given to be 5.00 GDMQ, and the relative molecular mass of A is 36.5 gmol, and this is equals to 5 divided by 36.5. We have 0.137. 0.137 mole per dm³. So my Ca is 0.137 mole per dm³. All right, next question says concentration of B in mole per dm³. So now we want to get the molar count of the base in mole per dm³. So my Cb here will be what? Now remember, you cannot say you're going to still use the same principle here, which is mass count over relative molecular mass. This mass concentration is impure. So for us to get a mass concentration which is pure, we use molar count times relative molecular mass. Therefore, we have to get the molar concentration through a pure form, not through the impurity. So we use the CABA to get our Cb. Thereby, we can proceed to get the mass concentration of the pure from there. So we are going to use CABA now in this case. All right, I'm taking out this. Now, the molar count of B we use CABA over CBVB is equals to NA over NB, where CB is equals to CABA-NB over VB-NA. And this is concentration of the acid is gotten to be 0.137. 0.137 mole per dm³. Volume of the acid is 19.1 cm³. Number of moles of the base is 1. While number of moles, volume of the base is 25 times number of moles of the acid is 1. So this is equals to, all right, we have 0.137 times 19.1 divided by 25, 0.105. We have 0.105 mole per dm. So I come here 0.105 mole per dm. So now we've got to the molar concentration of the base. Now we're going to proceed to get percentage purity. Now, how do we get percentage purity? Percentage purity can be gotten through a simple principle, which is the molar count times the relative molecular mass can give us that. Am I right? Now, we've gotten the molar count and the relative molecular mass can be gotten from here, so we can get the percentage, we can get the mass concentration of that, because the formula percentage is the mass count of pure over impure times 100, and we've gotten that of impure, so we must have to look for the mass count of pure first before we can proceed. So although that is not asked, they didn't ask us, but we should know in situations like that's what you must do in order to move forward. So I want to get the mass concentration of the pure base so that I can apply that formula when required. So let's go. I'm going to take this out. Now, mass count of pure B is molar count of B times the relative molecular mass of B. The molar count is gotten to be 0.105 mole per dm times the relative molecular mass here is 56 g mole. Potassium hydroxide. Potassium is 39 by relative molecular mass, plus oxygen is 16, plus hydrogen is 1. If you add that, you have 56 g mole. So 56 times 0.105. 56 times 0.105 is 5.88. So I have 5.88 GDN cube of pure B. So like I said, it must be lower than the impure. This is 5, that is 6 point. So GDN cube of pure is 5.88 GDN cube. Now we can get our formula. The last, we can solve the percentage purity. Percentage purity says that mass count of pure over mass count of impure times 100. So now I've gotten the required variables. If I apply that, I get what I want. So let's see. Let me take this out. Now, finally, percentage purity, which is mass count of pure, and that is 5.88 GDN cube over mass count of impure, which is 6.50 GDN cube times 100. And that is equals to 5.88 divided by 6.5 times 100 is 90.5. 90.5% pure. So that's very, very clear. So this we have again. We can always do this and all of that. So having gotten this, what's the next thing is you should calculate the percentage impurity. I want you to start doing that. Let me refill this. I'll be back. When I solve it, you know whether you get it right or wrong. All right. I guess by now you should be done getting the percentage impurity. So let's see, like I said, for us to get that, we just have to use the formula percentage purity plus percentage impurity equals 100, which means 100 minus 90.5 is equals to 9.5. So your percentage impurity is 9.5. So I don't know how many of you got that right. So, but let's proceed to solve more questions. All right, pick this up. All right, quickly, I think we should go down to water of crystallization, solve one question therein, and we can call it out for the day. The question says, solution A contains 20 grams of ethanediol acid crystals in 1 dm cube of the solution. Okay. A contains, this is H2C2O4. It says crystals. Let's go there. 20 grams of the crystals in 1 dm cube. So 20 GDM cube crystals. That is hydrated. I will explain that just in a minute. Solution B is a solution of sodium hydroxide. This time is sodium of potassium. NaOH, sodium hydroxide, containing 0.5 mole per dm cube. So Cb is 0.5 mole per dm cube. We should put A in a burette and titrate with a volume of 25 cm. And after that, we are going to get 41.63 as the volume of the acid. 41.63 as the volume of the acid. Now, if the equation of reaction is given to be H2C2O4 X water equals 2 moles of sodium hydroxide. This will give us our sodium carbonate plus our water plus our X water. Now, let me explain what has taken place here so far before we can proceed solving anything. Now, we say 20 grams per dm cube of ethane dioxide crystals. So, when we come to percentage of water of crystallization, we are saying that the salt or the acid contains a whole lot of water in it. So, our job, we want to find out what is the percentage of water present in that substance. And let me take, for example, this particular one here, H2C2O4 X water. Now, this is called hydrated what? Salt or acid, hydrated acid, because it contains water, and the number of moles of water are unknown. But if I take out this, I have H2C2O4. This is anhydrous. Anhydrous was water, acid, because the water molecules are out. Why am I making this distinction? Is because the formula says the relative molecular mass of the hydrated acid over the mass form of hydrated acid is equal to the relative molecular mass of the anhydrous acid over the mass form of the anhydrous, which means they have given us the mass form of the hydrated. We are going to calculate the mass form of the anhydrous. That is it. So how is all of this going to play? We are going to see, which means we are going to get the molar concentration of this, multiply that by days, which there's no water, for the molar for the mass form of the anhydrous. They're giving us this. The relative molecular mass of the anhydrous is, you can get it from here. That of hydrated will be gotten from here because it contains water. Take note of that, it's very important. All right, let's see what the question says. Haven't done that. Na here is 1, Nb here is 2. Okay, let's solve now. Question. Concentration of A in mole per dm. We want to calculate the molar concentration of the acid in mole per dm. Molar con of A. For us to do that, which formula are we going to use? Because we already having concentration of the base. So all the variables are given: volume of the acid, number of moles of the acid, same the other way. The only thing missing is the Ca, which means if we use the CAVA, it will be the most appropriate formula for us to get what we're looking for. So I have my CAVA over CBVB is equals to NA over N. I'm looking for CA. CA is equals to CBVBNA over VAND. If this is true, we move on to say concentration of the base is 0.5 mole per dm cube. Times volume of the base is 25 cm cube. Number of moles of the acid is 1. Volume of the acid is 41.63 cm cube times number of moles of the base is 2. So this is equals to, I have 0.5 times 25 divided by 41.63 divided by 2, 0.150. So I have 0.150 mole per dm. So that is, all right, that is the concentration of the acid. Ca is 0.150 mole per dm. Next question says, the number of water molecules in 1 mole of ethane dioxide. Now, they are taking us straight up, but there are a lot of other things we have to do to get to what they are asking us to do. So let me take this out and have more space. Now, the number of moles of water of crystallization for the hydrated. But remember, we are talking the mass count of the anhydrous. So now we can proceed to get that first before we can move on to do any other thing. So GDNQ of anhydrous will be, let's start. So now we'll say GDNQ, which is the mass count of A, is equal to the molar count times, okay, GDNQ, yeah, times relative molecular mass of A. Now we go. The molar count of A is 0.153 mole per DNQ times the relative molecular mass is 90 G mole. How do we get 90? The question will always come. H2C2O4. Hydrogen is 1 times 2 is 2. Carbon is 2 times 12, which is 24, plus oxygen is 16 times 4, which is 64. If you add all of that, you have 90. So that is how we got that. So 90 times 0.150 is equals to 13.5. 13.5 GDNQ. Oh, yes. 13.5 GDNQ. Remember, that of hydrated, it contains water. The mass count must be bigger than that of anhydrous when the water has been removed. So you can see the distinction is here. Key. So let's proceed now. How can we get the number of moles of water of crystallization, which they asked us to do, and hence percentage of what? Hence percentage by mass of water molecules. So first of all, for us to get the number of moles of water molecules, we now apply the formula. Remember that this which we've done, the reason why we say it is anhydrous is because we did not add X water here. If there is X water, it is hydrated. All right. The reason why it is 90, the mass count of the anhydrous, because there's no water therein. You're going to see the distinction in the two when I proceed further. So let's get the number of moles of water molecules present in the substance. So we want to know how many moles of water that are there in that hydrated substance. So let me put it this way. Now, okay. Number of moles, formula for number of moles of water present is equals to relative molecular mass of hydrated, I'm just going to call it hydrated, over mass count of hydrated is equals to relative molecular mass of anhydrous over mass count of anhydrous. Now the relative molecular mass of hydrated, this is the difference. Let me write them again so that you know. H2C2O4 is anhydrous. H2C2O4X water is hydrated. Now, we are talking of relative molecular mass of hydrated means I have to do the calculation of this. Remember, this is 90 and this water is 18. 16 plus 2 is 18. So, relative molecular mass of hydrated will be 90 plus X18. Is equals to relative molecular mass of anhydrous. This alone is 90 over mass count of hydrated. They gave us here 280 over mass count of the anhydrous. We calculated that. Where is it? 13.5. 13.5. So now we are going to make X the subject. So I will know the number of moles of water present therein. So for us to do that, I have to take a whole lot of waste out so that we'll be able to have more space. So, pardon me, you have this already, so it doesn't matter if I clean all of this. Number of moves, let's call it for us to make, okay? Number of moves of water would be, therefore, I cross multiply. This times this, what I'm looking for should be by my right. So I'll have 13.5 times 90 plus x18, close my bracket, is equal to 20 times 90, equals to 20 times 90. Now, 13.5 times 90 first. 13.5 times 90, I'm going to have 1215. 1215 plus 13.5 times 18. I'm going to have 243, 243x. This is equals to 20 times 90 gives me 1800. 1800. Now I'm looking for x, so I have 243x is equals to, I take this across the equality sign, which is 1800 minus 1215. Now 243x is equals to 1800 minus 1215 is 585. 585. Now, since I'm looking for x, I'll divide both sides by whatsoever is close to x. Divide both sides by whatsoever is close to x, which is 243. 243. This will cancel. My x is equals to 585 divided by 243 gives me 2.4. So 2.4. So the number of moles of water of crystallization is 2.4. Therefore, the formula becomes H2C2O4 2H2O. The nearest whole number is 2. So this is what the formula now becomes in the real sense of it. So this is ethane dioxide dihydrate because it contains 2 moles of water. All right, that aside, we've gotten our 2. They say hence percentage of water of crystallization. So we want to know the percentage of water that was present in this salt, in this acid. All right, I can take this out now. I guess so that we can proceed to get our percentage of water of crystallization. So let's go. Now, percentage of water present. Remember the formula is H2C2O4X water. Now I want to know the percentage of water is water over the total compound times 100. Percentage of hydrogen present here is hydrogen over the total compound times 100. The percentage of carbon is carbon over the total compound times 100. So you can see anything of this magnitude in your exam. You may come across something like calculate the percentage of carbon or of oxygen in that. So it becomes 04 over the total compound times 100. So in this case, we are looking for that of water because the topic says percentage of water of crystallization. So we're going to have X water over H2C2O4X water times 100. And our X was 2.4 times water is 18 over this, all of this is 90 plus 2.4 times 18 times 100. So this is 2.4 times 18 is 43.2. 43.2. So this is 43.2, therefore this is 43.2 plus 90. Plus 90 is equals to 1332 times 100. Now this is 133.2. Okay, good. We have 43.2 divided by 133.2 times 100. The percentage is 32.4%. So you take that as your maybe assignment or something to calculate the percentage of carbon. We just did that for water, percentage of water in that compound, which is the total water over total compound times 100. If I say that of carbon, it will become C2. Carbon is 12 times 24 over 133.2 times 100. If I talk of oxygen, oxygen is 16 times 4 over 133.2 times 100. If I talk of hydrogen, is 2. 1 times 2 is 2. 2 over 133.2 times 100. So by this, we are coming to a close. It is important that everything which we discussed today is expediently important. We need to know our formulas, know how to apply them, various variations of the formula, because if you know one and you don't know the other one, and the other one is required for you to solve a particular problem, you wouldn't get it right, so you're going to fail. So the number one thing first which you have to do is to know the number, all the formulas that are required for percentage purity, water of crystallization, amount, related molecular mass, and all of that. 2, if you have not subscribed, then you're going to be missing a whole lot, because when I drop a video, you wouldn't get it. So I advise you subscribe and take your time out to watch, study, ask questions when required and when necessary. Send your question to the platform. I'm going to attend to them when I see them. And by so doing, I guess we are going to be fine. Do have a beautiful time. Don't worry.